All right, so section 6.2 is about addition and subtraction of rational numbers. And now we're going to take a look at multiplication and division of rational numbers. Okay? And what we're first going to start with is the idea of multiplication. So if we have a over b times c over d that are rational numbers, okay, so that means, again, that we have the ability to change them if they aren't already this way, but we have the ability to have them be written as an integer over an integer. And we want to multiply them together. Multiplication is easier than addition, because all you got to do is multiply across the top, multiply across the bottom. Multiplication is easier than addition. Now, what I'd like for us to take a look at is a justification in terms of a diagram of why that makes sense. So we're going to use a rectangular region to illustrate what 3/5 times 3/4 is equal to. So we're going to draw what's called a fraction bar, which is in essence a rectangle. So make yourself a rectangle on your paper. You can make it long and skinny, short and fat. It really doesn't make any difference. Just draw a rectangle. And we're going to split it vertically. Okay? I'm going to try and draw, let me get that, this fraction 3/5 with the rectangle. So I'm going to make, how many boxes am I going to need? How many vertical bars? 5. And how many am I going to shade in? 3. Okay, so I'm making 5 vertical bars and I'm going to shade in 3. So here's 1, 2, 3, 4, 5. And they should be equal in size. Mine are close. And it's just a shade in 3. That's 3/5, agreed? Okay, we're going to do the same thing now with the 3/4, but we're going to do it horizontally. Okay, so we're going to make, so I know your picture has, well, mine has blue on it. We're going to just, in our minds, ignore the blue. Are you with me? Ignore it. We're going to draw it horizontally. So, how many horizontal rows do I need? 4. Okay, so we're going to split it. I'm going to use red on this one. And again, they should look equal, and mine are less equal than they were last time. Okay, I'm a little happier with that. Not a lot happier, just a little. All right, and so again, ignoring the blue in our mind's eye, ignore it, okay? We're going to shade however many rows we need. How many rows do I need to shade? 3, because it's 3/4. So I'm going to shade 3 rows. Everybody have a pretty picture with some shading, or maybe you did your cross hatches different direction if you're using a pencil or pen. So here's my question to you. How many boxes are double shaded? 9. How many total boxes are in my picture? How many? 20. In the whole picture, it's 20. That's the 9 and the 20 we get when we multiply, right? 3 times 3 is 9, 4 times 5 is 20. 9 out of 20. Okay. I've had some textbooks that I've used when I've taught this before that don't do the shading quite like this. So let me show you one other way to think about the shading, and I'm going to do it by undoing something I already did. Okay, so I'm going to go back to my 3/5 picture. Just watch with me. Your book does what I just showed you. But the other option is that you can sort of ignore the whole the diagram as a whole, and the only portion of this picture that's in your mind that you're using at this moment now is the picture that has the blue squares in it. Okay, so just pretend you only have the blue squares. You still have 4 rows, agreed? Okay, so you're still going to shade 3 of the 4 rows. So this is like saying, you know, you have a cake, and somebody already ate 2/5 of the cake. So the only thing that even makes sense to talk about is the 3/5 that's left over. You know, the only thing that my husband brought home was the 3/5 of the cake that was left over. And then if we talk about somebody eating 3/4 of that piece, those pieces of cake, what did they eat 3/4 of? Well, only the blue pieces, right? Because those are the only pieces that were still left. So how many pieces did they eat? Well, 9. But that was 9 of how much of the whole cake? 20 slices. So you can think about it from that perspective too. If you want to use this diagram where you don't completely finish shading, that's fine. If you want to do the double shading and see and count that way, that's fine as well. Either way works. All right, so let's take a look at some more information in this section. Identity and inverse, a multiplicative identity. The number 1 is the multiplicative identity, and we encounter this well before we ever get to rational numbers. Whole numbers, it works, right? We have whole numbers, we have the number 1. Natural numbers, we have the number 1. 1 is simply the number that we can multiply things by, and it doesn't change anything. It's a very unexciting number, to be honest. So if we do 1 times a over b, it's the same thing as having a over b times 1, and it equals a over b. A multiplicative inverse. Now this is unique. When you only have whole numbers, you don't have this at all. A multiplicative inverse is the number you multiply by to get back to the value of 1. There's a couple names for what you've probably heard this described as. One of them is actually called multiplicative inverse. What else have you heard this described as before? Reciprocal is a real common one, yeah? There's one other that I sometimes hear students say. Does anybody else have it called something different? Sometimes I hear students call it the flip. It's the flip of the fraction. It's the fraction flipped upside down. So I sometimes hear that language used as well. That value is a unique value, right? There's only one that works. So no matter what number you give me, I can only give you back one answer that's the multiplicative inverse. It is unique. Now, it's true that if we're working with the rational number system, that if I also have a whole number, like 3, what would be its multiplicative inverse? 1/3. Because we have to remember that 3 is the same as really 3 over 1, right? What if it were negative? What I gave you -3? What would it be? -1/3. We'd need the negative in order to cancel it out to give me back to a positive 1, right? Okay, so keeping a couple of those things in mind. We're going to go through with some more properties next. Next property is the distributive property. So these are theorem 6.11. There's several properties in them. 6.11. The distributive property of multiplication over addition says that if I have a over b and I want it to be multiplied by c over d plus e over f, I could distribute it across the multiplication before I actually added or subtracted. It would be okay if this said addition or subtraction actually. So we have the ability to distribute or to multiply through the parentheses. All right, the next one is the multiplicative property of equality. And it says if I have 2 equal fractions, a over b equals c over d, and I have some other fraction, and I multiply each of my fractions by that value, they're the same as they were before too. They're both equal to each other. We talked about this kind of an idea, this property of equality with addition, right? If I add the same number on both sides of an equal sign, if I subtract the same number on both sides of the equal sign, it doesn't change the fact that both sides are equal. Same thing's true for multiplication. Inequality, much the same, except that there is a nuance. There's some slight difference. That's why there's 2 properties here. The first one says if you have a over b and it's greater than c over d, and notice this says that e over f is positive. If you have a positive number, and you multiply by that positive number on both sides, then the inequality, let me get the word right, stays the same. If it was greater than to start with, it's greater than to end with. If it was less than to start with, it would be less than to end with. But if you multiply by a negative fraction, or a negative value, really, it changes the direction of the inequality. Did you guys catch that? I know you probably remember that, but it might not be a bad idea to justify a why. So let me just use some whole numbers to show you and remind you why this works. Let's say you have 2 and it's less than 3. And everybody's good with that so far, right? And let's multiply both sides by -4. So on the left I get -8, and on the right I get -12. Which of these numbers is bigger? -8. And it always feels a little funny when it's negatives, but you try to remember the number line, okay? Big negative numbers are on the far left, right? So like the -12's on the far left. -8 is a little bit, I'm sorry, my left, your right. No, left, I said it correctly. This is what happens when I'm turned around in classrooms. Okay, your far left, and if you move a little bit to the right, you actually get numbers that are a little bit less negative. That's where the -8's going to lie. And a number that's a little bit more to the right is going to be a bigger number, right? So the -8 is larger, and what we want to notice, of course, is that the direction of the inequality changed in order to make that statement actually work, to make it true. All right, we're going to do an example using some of these properties, and as we do this example, we're going to identify the properties that we used. We did this with addition and subtraction last time. Now we're going to do this with multiplication and division. I'm sorry, I had one more property. I'm all ahead of myself. I'm sorry. One more property. Property is 0. Okay, if we multiply by 0, what happens? It's very exciting. It turns into nothing. Fabulous. Okay, now we're ready to do what I was wanting to do. Solving for x. Identify each property used in your solution process. All right, our goal is to get this to say x equals something. Okay? So we have this 3/4 that is right now somehow attached to the x. How is it attached? It's multiplied, right? That 3/4 is multiplied by the x. How then do we unattach it? We either divide or we multiply by a reciprocal, right? Which is the same as the division. What is the reciprocal of this? 4/3. So why did we choose the reciprocal? Right, because it's the multiplicative inverse. So we're using the multiplicative inverse property. That's why we chose the 3/4. Now, the fact that we multiplied, that we actually had the ability to multiply on both sides of the equal sign is another property in and of itself. What is that property? What is it that allows me to do that, to actually put the 4/3 on both sides and say I'm going to multiply? Yeah, it's the multiplicative property of equality. And then, when we multiply 4/3 times 3/4, we actually get the number 1. And I know you probably never actually write that down now, but that's really what happens, right? 3/4 times 4/3 is actually really 1, and that's the multiplicative inverse going on there. On the other side, we have the 1/5 times 4/3, which becomes what? 4/15. Okay? And then, so in some reality, I think probably we could have written these in the other order, maybe a little bit nicer. Okay, that wasn't what I wanted to do. Let me try that again. So the multiplicative inverse is what turns that into the number 1. The multiplicative property of equality is what allows us to multiply on both sides. Okay, and then what is 1 times x? X. And that's actually a property as well. So what is the property that says that 1 times x is x? Anybody see it? That is the multiplicative identity property. The multiplicative identity property says when I multiply by 1, nothing changes. It's the same as it was before. So 1 times a over b is a over b. 1 times x is x. Okay? We're going to do another one, a little bit more complicated. 2x/3 plus 1/4 equals x/6 minus 1/2. We have so many different options of what we could do first. What do you guys want to do first? Don't everybody answer at once. Okay. So which side would you like to move them to, Catherine?
Let's move x/6 over to the other side.
Okay. How are we going to move them?
So we can, first off, make the denominator 2
Okay,
Like the numeration over by 2.
but how are we going to move them? Like what operation?
We have
First.
to subtract.
Subtract. Okay, let me do that first. We'll get the common denominator in a minute. You're right, but let me do the subtraction first. What operation, or what property rather, is it that allows me to do a subtraction on both sides?
Isn't it equality?
Yeah, it's a property of equality. It's called the additive property of equality. We're adding a negative, actually. And why in the world did we choose the negative x over 6 to actually be added to both sides?
Because you want the x's on one side so that you can set them equal to something and figure out what they are.
That's true, but how will that make this?
Oh, it makes it like when you times it by the same thing, like when you subtract it from
Subtract
one side,
it.
it goes away. Sorry.
Okay, so what is that called when we subtract something from itself? It had a name. It was back in section 6.2. It's an inverse. It's the additive inverse, right? Exactly. So this is the additive inverse property. And when we subtract them, we usually don't actually write it down, but really what happens when I take x over 6 minus x over 6 is I get 0, right? So what is it that makes the 0 and the negative 1/2 become just negative 1/2? So let me actually write what I'm thinking so that you can see it. That's the additive identity. So right now, this is what I have. I'm not dealing with the 1/4 and the 1/2 at the moment. But the fact that that became 0, and then in a minute here it's going to go away entirely, is going to be the additive identity. Okay, can I do something with the 1/4 and the 1/2 at the same time? Are you guys okay with that? What could I do?
You can subtract the 1/4 and add it to the other side to the 1/2.
Okay, so like basically the same operation that I already did, but with the number instead of with the variable term, right? So this is actually now a 0 right here too. And I now have a minus 1/2 and a minus 1/4. And again, if I were being really clear and detailed and super careful, I could write this without the zeros. And the fact that I have the ability to write it without the zeros is that additive identity property that we were talking about just a moment ago. Some of you are like, man, didn't realize I was using all those steps at the same time, and you were. You were. All right, so we had mentioned before, Catherine, you had mentioned wanting to get common denominators, right? What would you like your common denominator to be for 2x over 3 and x over 6? 6. So the first one will have to be multiplied by 2 over 2, right? What would we like our common denominator to be with 1/2 and 1/4? 4. So we're also going to multiply by 2 over 2 to the 1/2. Okay, so now I've got 4x minus x over 6 equals negative 2 minus 1 over 4. Now what?
Wait, why did you do negative 2 minus 1 over 4?
Why is it over 4?
Yeah.
Because I got a common denominator right here at that point, yeah. All right, 4x minus x is 3x over 6. Negative 2 minus 1 is negative 3 over 4. Okay, so all I'm doing right now is just combining like terms, simplifying fractions. So if you want to write that down as the reason, that'd be totally acceptable. So we're just combining like terms. You could say simplifying. Okay, now what am I going to do? Okay, we could reduce or we can cross multiply either way. So what do you guys want to do? Reduce first and then cross multiply maybe? Let's try that. So if I reduce, this becomes x over 2, right? Equals to negative 3 over 4. Okay, that's actually the fundamental property that we encountered last time, fundamental property of rational numbers. I think we encountered it in section 1 actually, not even in section 2. It says that I'm allowed to either multiply or divide, but anything I want as long as I do it on top and bottom. That's what I used. All right, then you guys want to cross multiply. Can I convince you to do something different? Because see, if you cross multiply, you're going to have one more step. But there's something else you could do instead that will make the problem finished.
Multiply by 2.
You could multiply by 2. Why 2? But I don't want to multiply by 2 over 2, which would give me a common denominator. I don't really want a common denominator. Yeah, so like it's 2 over 1, right? So what is 2 over 1 when compared to 1 x over 2? Why am I using 2? What's it called? It's called the inverse. It's a multiplicative inverse, right? The multiplicative inverse, I know we don't have it written that way, but what we really have here is not x over 2. We really have 1 half x. I mean, that's what it really is. So it's the multiplicative inverse of 1/2. So we've chosen to use here, multiplying on both sides is the multiplicative property of equality. So let me copy what I had on the other page going on over there. Is it 3 over 4? Negative 3 over 4. Okay, and again, technically 2 over 1 times 1 over 2 is 1 x. Why?
Because when you do it by the inverse, it equals 1.
Right, it's a multiplicative inverse. And then 1 times x is, well, x, right? I guess I could have simplified the left right-hand side. What does this give me over here? Maybe 6 over 4. Okay. So I got x on the left because that's the multiplicative identity, right? And then what happens when I have the negative 6 over 4? You can reduce that. So that's negative 3 over 2. Am I okay to leave the problem as negative 3 over 2? I am. I don't need to worry about mixed numbers. I wasn't asked the problem mixed numbers, so I don't need to get it into mixed numbers. And so again, that's the fundamental property or principle. I don't remember how your book describes it, but the fundamental principle of rational numbers. Okay, any questions on that one? See. All right, we're going to do a couple more examples and then we'll pause for today. Division of rational numbers. If we have a over b and c over d and they're rational numbers, and a over b divided by c is equal to e over f, then this will be true if and only if e over f is the unique rational number such that c over d times e over f is equal to a over b. This is not like the how do we do the division. This is the definition for what division actually means. And again, we've seen this before with whole numbers, many of you, but all this is really saying is, let me use a bigger number, 6 divided by 2 is equal to 3. And if that's true, the only reason it's true is because 6 is equal to 2 times 3. They're showing it in terms of rational expressions where you've got fractions involved, but it's the same thing. Okay, that's all this definition says. That is usually how students first learn to do division. They've already learned their multiplication tables, and then somebody is starting to try and help them think about it backwards. You know, they know that 2 times 3 is 6. So when they learn what is 6, they think 6 divided by 2, what is times 2 that equals 6? Oh yeah, it's 3. Okay, same idea. And this is actually the algorithm for how we do it now. And I want to talk to you in this slide about why. So the algorithm for division, if you have a over b divided by c over d, it's the same thing as having a over b times the reciprocal d over c instead of c over d. So what you see happen is you see the fraction flip, you see the division become multiplication. Okay? This is one of those things I think that a lot of people just think, okay, fine, I can remember how to do that, and I can remember it works, but why? I mean, it feels a little bit like magic, okay? And it's really not anything magical about it. So let me show you why it works. So when you have that one kid that asks you, you'll be like, wait a minute, let me go get my notes and I'll talk to you tomorrow and I can show you why. So let's say you have A over B divided by C over D. And what I'd like to do, that is an A, it doesn't look like one, but is I'd like to rewrite it as a double fraction. So I'm going to write A over B over C over D like this. So these are called, it's called a complex fraction. Okay, when you have a fraction inside of a fraction, it's called a complex fraction. I would like the C over D to not be there, and that's what's making it complex. It's a second fraction involved in the problem. Well, the way that I get rid of C over D is I use the reciprocal because it's a multiplicative inverse. And I do that because then that C over D times the D over C in the big denominator down here becomes what? 1. My numerator becomes the A over B times the C over D. And then when I divide by the number 1, what happens? It stays the same. So I have A over B times C over D. And you'll notice where we started was division. Where we ended, I'm sorry, I wrote it wrong. Nobody caught me.
Yeah, I was wondering.
Oh, you guys, please tell me if I screw stuff up. It'd be really helpful so that I don't make anybody else more confused than I am. D over C. Alphabetical order, I just want that C on top. Man. All right, there it goes. So if you compare, which is where I was trying to do, where we started to where we ended, that's the algorithm above for the division. Okay, I want to do one more example before we stop, and the next place stopping spot's a really good one anyway. This is something that is not a part of this particular course, but it will help us to understand what we do on the next one. So it says to describe what is meant by 6 divided by 2. Show a diagram to support your description. So when we have 6 divided by 2, can somebody kind of give me a word description, like with an example, like, you would tell a child with context. What does 6 divided by 2 mean?
So if you have 6 people and you're going on a field trip and you're taking 2 vans, you need to figure out how many of those 6 people need to go in which car.
Okay, so one way to describe it is that you have 6 objects and you need to split them into 2 groups. Does everybody get that description? Okay, there's another way to describe 6 divided by 2. Any ideas about what that might look like?
You have 6 things and you need to put them each in groups of 2. How many groups
Okay.
of 2 would you have?
Awesome, so that's the other description. These are called set division or set partition, if anybody remembers from elementary math 1, number theory. So the second way to do it, as Leah said, is that we would take 6 objects and we would put them into groups of 2. That's the description that I'm going to use because it fits more nicely into where we're headed with it. But the other description is the one we usually think of first. So imagine taking 6 objects. I'm going to use circles just because they split up into objects that don't look quite so much alike. So I have 6 circles. And I'm going to put them into groups of 2. And the question is, how many groups of 2 do I have? And the answer is 3 groups, right? So 6 objects, groups of 2. How many groups do I have? 3 groups. Now, we're going to use that same idea. We're going to draw our 6 circles that we just drew, but we're going to divide by 1/2. I don't want groups of 2. What do I want groups of? 1/2. How many 1/2 of circles do I have? 12. I think cookies is a good picture, like the big giant cookies that you see at places sometimes, like McAllister's, right? Big giant cookies, 6 of them. And you want to know how many halves of cookies do you have if you have 6 cookies? You have 12 halves. It's not because you're dividing by 2. In fact, you're not dividing by 2. Dividing by 2 would give you an answer of 3, right? You are not dividing by 2. You are taking your diagram and you are making groups of size 1/2. This doesn't work very well with people. Don't try that. That doesn't work. So we can't do our people on our buses on this one, right? Because we would have halves of people. But cookies work very nicely. So we have 12. It sounds funny to say it, but we're going to call it groups of size 1/2. And that's why it makes sense to talk about this being 6 times 2 over 1 and it becoming 12, right? The answer is supposed to be 12 using that algorithm that we just developed on the previous slide. It should be 12. And here's why. Here's a picture as to why it works too. A lot of people need pictures to make sure that they understand the ideas.